Hello and welcome to another video in this series as we journey from the very simple primes to the foothills of one of the most important challenges in mathematics, the Riemann hypothesis. Now up to this point we've been exploring prime numbers and looking at some of their properties, and overall we've found that they are quite difficult to encapsulate in a simple mathematical formula. They seem to resist attempts to find patterns in them. We did take an experimental approach where we saw that there was an approximate formula for the number of primes up to x, and that was very compelling, but that's not proof. So today we are going to look at a mathematical relationship which Euler discovered between ordinary numbers and the prime numbers. It was quite an advance, and even today it's still quite an amazing achievement, and yet it isn't actually very difficult to kind of recreate, so we're going to do that today. So just to restate that, Euler was the first to find a simple, whatever that means, connection between the primes and the integers. So we'll start off with some of the basics that we've already covered, because those foundations are what we're going to build on. So let's look at some things we've already talked about in previous videos. We know that the harmonic series 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, we know that diverges. And we've talked about that, and we've kind of given a proof of that as well. We also know that the sum of inverse squares, 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, we now know that converges. It wasn't immediately obvious, and in fact it was a very difficult challenge, which was actually solved by Euler and made him famous. It was known as the Basel Problem, and in a separate video we look at that and also show how Euler did it, and just as a nice reminder, it sums to pi squared over 6. So if this one diverges and this one converges, it's natural to ask, well, what happens if we change the power? So the power here is 1, the power of n here is 2, what about 3, 4? And we can write a general expression. So instead of just 1 over n or 1 over n squared, we can say 1 over n to the power of s. So we've introduced a parameter which we can tweak called s, and we can write that out, this infinite sum of 1 over 1 to the s plus 1 over 2 to the s plus 1 over 3 to the s, and so on. So when s is 1, that's the harmonic series that we know about. When s is 2, it's the Basel problem that we know about. But s could be other numbers. So it's an interesting question to ask, for which values of s does this more general series converge? And this series will pop up a lot. It's quite an important series, and the thing is given a name, the Riemann Zeta Function, and you'll see that popping up. And in fact, the Riemann is the name given to the famous hypothesis that we're ultimately in this series of videos trying to kind of start to understand. So you can imagine this function has got a lot to do with that very famous and as yet unsolved problem. So this is the Riemann Zeta function, which is simply a generalization of the series that we were looking at before. We can now say s is 3 or s is 2 or s is 0. So if s is 0, this series turns into 1 plus 1 plus 1 plus 1 plus 1, and we know that diverges. If s is 1, it's the harmonic series, and we know that diverges. If s is 2, it's the Basel problem, and we know that converges. And series like 1 over n cubed or 1 over n to the 4, when s is 3 and s is 4, they converge as well, and we don't need to work very hard to understand why, because if we compare them to 1 over n squared, the Basel one, each of the terms in these series is smaller than this one. So we can easily say that if this one converges, so do these, because the terms are all smaller than the corresponding ones in this one. Let's draw a picture to understand that. So we know that 1 over n squared converges, and that's 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, and so on. And we want to ask, does 1 over n cubed, if we do the infinite sum there, that's 1 over 1 cubed plus 1 over 2 cubed plus 1 over 3 cubed plus 1 over 4 cubed, and so on. Now if we know this converges to pi squared over 6, if we ask, does this thing converge? Well, we can say it does. We can't yet say to what, but we can say it does, because each term, we can match them up like this and say, let me change colour. We can say this one is smaller than that one, and this one is smaller than the corresponding one, and this one is smaller than the corresponding one, and we can do that systematically for all the rest of the series. So if this converges, then we know this one does, because each term is smaller, and therefore the sum that it converges to will be smaller as well. So that kind of comparison is really powerful. It's easy and it's powerful, but it doesn't help us answer to what value it converges. But often that's not what we want to do. And the same applies to 1 over n to the 4, when there's the zeta function for s equals 4. Again, each term is smaller, so that too will converge. So we can see from that logic that when s is 2 or larger, the series will converge. But less obvious is when s is less than 2. We know that when s is 1, the harmonic series, that diverges. We know that when s is 0, that the series turns into 1 plus 1 plus 1 plus 1, which diverges. But what about 1.5, 1 2/3, 1.785? That's not so obvious. And in a separate little video, which I'm recording straight after this one, we'll show a very short proof that the Riemann Zeta function converges when s is more than 1. We'll show that, and it's not that difficult to show, and he uses this same idea of comparison. So definitely do watch that. I won't do it here because it takes us away from the main thread. So for now we know that the zeta function converges as long as s is more than 1. So 1 it doesn't, but 1.1 it does. So let's derive this magic kind of connection that Euler came up with, and we'll do it by writing out the zeta function again, and we'll notice that 1 over 1 to the s is just 1 as long as s is more than 1. So we can just simplify that to 1. So it's 1 plus 1 over 2 to the s, 1 over 3 to the s, and so on. We've just written it out again. There's nothing magic happening there. Now if we divide this series by 2 to the s, each of these terms is divided by 2 to the s. So we end up with 1 over 2 to the s times the zeta function equals 1 divided by 2 to the s plus 1 over 4 to the s plus 1 over 6 to the s. And you can see these are now multiples of 2 to the s. And they look like 2, 4, 6, 8, 10. So all these denominators are multiples of 2 to the s. Now what we're going to do is we're going to subtract this from this. In effect, we're going to take out these terms which have multiples of 2 to the s as the denominators, we're going to take them out from this full list of numbers. It's like a sieving process, and there are parallels between what we're going to do and the Sieve of Eratosthenes, which you probably have kind of looked at when you were young in school as a very simple way of finding prime numbers, manually. We'll look at that at the end of this video again. So let's do that subtraction. So we've now got the original series minus 1 over 2 to the s of the series, and you can see we've removed all those terms that were multiples of 1 over 2 to the s. In effect, we've removed all those things that had even numbers in, as we've sieved them out. So that leaves the odd numbers here. That's nice and easy to see. Okay, let's continue. By the way, it's worth saying that this dividing and subtracting of infinite series, we usually have to be quite careful. I know we're doing it casually here, but it's only valid because those series are convergent, absolutely convergent. If they weren't, then we'd have to be really careful, or what we did might not be valid. You can't have a series which is divergent and then do these kinds of manipulations like halving it and adding it to itself and so on. So now let's see if we can do the same thing again. Now, looking at this, we've taken out multiples of 2 to the s, and we're now left with something with odd numbers. Let's take out multiples of 3 to the s, and we do that by dividing this whole thing by 3 to the s and going through that same process of removing it from this. Let's write that out so you can see. So this is that previous series divided by 3 to the s, and we end up with 1 over 3 to the s, 1 over 9 to the s, 1 over 15 to the s. Now 1 over 6 to the s isn't here. This might look like the multiples of 3, and they are all multiples of 3, but not all of them. So for example, 1 over 6 to the s is not here because that would have required us to have 1 over 2 to the s times 1 over 3 to the s, and 1 over 2 to the s was removed in that previous step. Right, so if we now take these from the previous series, so we end up with this thing, and we're left with 1 plus 1 over 5 to the s plus 1 over 7, 1 over 11. And you can do this yourself, pen and paper, and I really do recommend it because the mechanics of doing it give you a feel for what we're actually doing in this sieving process. You might start seeing a pattern here. You might start suspecting, well, hang on, we had 3 here, got 5 here, 7, these are prime numbers. They're not all prime yet, but there's something definitely related to primes going on here. So now we've sieved out the multiples of 2 and 3 to the power s. We might think, well, let's now remove multiples of 4 to the s, but we can't because they were already removed when we removed multiples of 2 to the s. They're not there. So let's look at that list again. In here, there's nothing that's a 4 to the s or a multiple of 4 to the s. So there's no 8 or 12 or 16 because they were actually also multiples of 2 to the s. So they've already been removed. And I'm lingering on that because that's kind of important insight as to what's going on. So the next useful thing we can do is remove multiples of 5, which is a prime, 4 isn't. And if we do that, we divide that series by 5 to the s and then remove it from the previous one. We end up with this on the left hand side, 1 minus 1 over 2 to the s times 1 minus 1 over 3 to the s, 1 minus 1 over 5, 2, 3, 5. That looks like prime numbers to me. Equals 1 plus whatever we've got left. Remember, 1 always survives, and the others get progressively chopped out. So at this stage, when we've done the 5, we're left with terms whose denominators are not multiples of 2, 3, or 5, or 4, because that counts as 2, So you can see 6 won't be there because 6 was removed. Multiples of 6 were removed when we removed multiples of 2. So the next one is 7. So you can see why we are removing successive primes. If you do this yourself, pen and paper, you'll notice two things. We can only remove multiples of successive primes. So the first step was multiples of 2 to the s, then 3 to the s, then 5 to the s, because 4 was counted in 2. There's no 6 to the s because that's 2 and 3. 7, there's no 8 to the s because that's 4, or 2 and 2 and 2. Same with 9 was already done by 3. 10 was done by 2 and 5. 11 is a prime. I really encourage you to do it by pen and paper, just yourself, because the act of doing it helps this idea sink in. Me just talking about it doesn't work as well. And after each removal, the very first term always survives, because we're doing 1 minus multiples of other terms. So if we carried on forever, on the left hand side we'd end up with 1 minus 1 over 2 to the s times 1 minus 1 over 3 to the s times 1 minus 5, 2, 3, 5, 7, 11, all the primes forever. And on the right we'd have removed everything except 1. That's all that would be left, because every other term would have been removed, because it is either 1 over prime to the s, or it has factors which are primes. So on the right the only thing that will remain is 1, and on the left we'll have the zeta function times this infinite product, and that's easy to rearrange. We can just isolate that zeta function on its own, and we end up with the product. So this symbol is like the sigma for sum, and this kind of big pi is a product symbol, and it means and here we mean the product over all the primes. 1 minus 1 over p to the s, that's inverse. So that's interesting, because if we write that out again, because remember the zeta is a sum, we have Euler's product formula. This is the important connection between primes on this side and normal counting numbers, the integers, on this side. And that's interesting, because we thought for so long that there was not an easy way of connecting the patterns in the primes. We couldn't, they weren't like the even numbers which are 2n, or the triangle numbers which are n times n plus 1 over 2. There wasn't an easy formula, and still this doesn't give us a formula for the nth prime, but it does encapsulate some other deeper connection. It's amazing that we have a closed form, a formula we can write down in a few symbols that connects all the primes with all the integers. It'd be great if we had an even simpler formula, of course, but this is still a massive achievement, and actually the derivation of it didn't require advanced maths at all. It just required us to be a little bit careful about infinities, but we didn't need to do anything more than understand what multiplication was. So that's amazing. This is a connection, a bridge between the world of ordinary counting numbers and the world of primes. Now this is often a starting point for research or kind of investigations into primes and other elements of number theory, and in the next video we'll also explore a few simple things that pop out by walking across this bridge between the primes and the integers. I'm calling it a golden bridge for now, and some of the things that pop out are really, really nice and easy. When I first saw it was quite a shock that something as elusive and difficult as the primes was actually in the end able to be captured in a formula like this. So we will explore this further, and the Riemann Zeta function we will explore a lot more much further down the line, because the Riemann hypothesis, the famous problem, is centered around that. fantastic. So I hope you enjoyed that. As I say, it is definitely worth going through that derivation yourselves, pen and paper, because the mechanics of doing it will show you and give you a feel for what's really going on with that sieving process. What I'm going to do now is just compare that sieving process with the famous kind of sieve, the Eratosthenes sieve, which many school kids learn about, just to see the comparison. So I'll do that now. So we have here a number grid, and what you might have done in school as a young person is be introduced to something called the Sieve of Eratosthenes in ancient Greek, and it was a way of discovering or identifying prime numbers. And what the method was simply, by the definition of the primes, they don't have any factors other than just themselves and 1. So the idea was to go through the numbers systematically and say we exclude 1, and we say we pick on 2, keep that, and then we cross out any multiples of 2. So all the multiples of 2 are the even numbers, like that, and so on. And we could carry on. And then we look at the next number 3 and keep that, and then we cross out multiples of 3. So 6 is already crossed out, 9, 12, 15, 18, 21, 24, 27, 30, 33, 36, 39, and so on. So far we've got 2 and 3 as the prime numbers. We look at 4, that was crossed out, so we won't continue with that. It's not a prime number because it was a multiple of something else. Now look at 5, that wasn't crossed out, so that's our next prime. We've recovered. And then all the multiples of 5 are crossed out. 10's already crossed out, 15, 25, 20, 30, 35, 40, and so on and so on. And then we look at 6, that's already crossed out, 7, that's the next prime. And multiples of 7 are 14, 21, 28, 35, my brain's not working, and then it's 42 and so on. Great, so 7's pulled out, and then we look at 8's crossed out, 9's crossed out, 10's crossed out, 11 is next. And multiples of 11 are 22, 33, 44 and so on. 12's crossed out, 13 is next. And multiples of 13 are 26 and so on. So you can see how this can give us the primes, and it's a manual process. It's not efficient for finding large primes, but for a school child's kind of fun exercise, it's interesting, and it's useful to do manually at least once or twice, because you can see this sieving action in motion, and the sieving is a representation of what a prime is. It's not a multiple. So by chopping out the multiples and keeping what isn't a multiple, we're recovering the primes. So that's what the Sieve of Eratosthenes does. Let's look at what we were doing. So we started with the Riemann Zeta function, which has terms with denominators 1, 2, 3, well, 1 over 1 to the s, 1 over 2 to the s, 1 over 3 to the s, 1 over 4 to the s, and so on. So all those integers really. And then we were subtracting all the ones that were multiples of 2, that were multiples of 2 to the s. So we were chopping out all the multiples of 2. We weren't keeping anything, we were just chopping them out. So that removes all the even ones, like that, and so on. Do a few more, you can obviously carry on if you want. So we were left with a series where the terms had odd numbers. There was 1 over 1 to the s, 1 over 3 to the s, 1 over 5 to the s, and so on. And then what we did was, well, let me just keep track of what we're doing. We had zeta s, a funny squiggle, and then we said 1 minus 1 over 2 to the s times that, left us with what we've got here. And then we said let's remove all the terms which were multiples of 1 over 3 to the s. So what we were doing there was saying 1 becomes 3 to the s, and we chop that out. What else was remaining? 3 was remaining, and that became 9. 3 times 3, 9. Let's just mark them for removal. 5 became 15. 7 became 7 times 3, 21. 11. So 9 became 18. 9 times 3 is 21. 9 times 3 is 27, sorry. And 11 times 3 was 33. So that was removing those. And then we said from the ones that were remaining, we remove the terms that are those but multiplied by 1 over 5 to the s. So that became 5 to the s, which we removed. This one was remaining, 5 times 5, 25. That one was removed. 7 times 5 is 35, so that was removed. And so on. So you can see how what's left for us to pick on are those primes. So the next one will have to be 1 over 1 to the 7 to the s. So 1 becomes 1 over 7 to the s, and that's marked for removal. 7 times 7 becomes 49 over here for removal. So you can see by doing this we are eventually chopping out everything. We're not keeping anything. So it's very similar to the Sieve of Eratosthenes, but there we keep the primes, here we don't. And you can see how by doing this we eventually remove everything and keep, the only thing that's left is 1. And that's why this thing, when we keep doing all the primes, becomes 1 on the right hand side. So just going through that exercise helps understand the mechanics of what those algebraic manipulations are doing. Fantastic. Well, I hope that was useful, and it's a surprisingly simple derivation of a quite deep and kind of important formula. Do watch the associated video where we prove that the Riemann Zeta function converges for s is more than 1, because it introduces a very powerful technique, a simple technique, which is also used a lot in number theory, called integral comparison tests. See you for that one. Bye.